So we've dealt with weak acids and weak bases and their ability to either donate or accept a proton. So now what we want to do is we want to actually look at polyprotic acids. So polyprotic acids, if we look at the word, poly means more than one, and then protic, so we have multiple proton acids. So what we're going to see here is whenever you have a polyprotic acid, this will be whenever an acid has two or more protons, the acid actually dissociates one proton at a time. So what we'll do to differentiate between the different steps will be to denote it as Ka1 or Ka2. But again, whenever we look at this dissociate in a stepwise manner, what this is just saying is we're removing one proton at a time. So if we look at our first example of carbonic acid, H2CO3, what happens is at first carbonic acid loses one proton. So this will end up forming its conjugate base HCO3- and the hydronium ion. And we can see that Ka of this first step is 4.3 times 10 to the negative 7th. And then there's still another proton. So this conjugate base can now behave as an acid. So here, HCO3- again loses another proton, and we're left with hydronium and carbonate. So what we'll end up seeing is, let's compare the Ka values. Okay, so we have Ka for the removal of the first proton and Ka for the removal of the second proton. Notice that this is on the order of magnitude 10 to the negative 7th, and this is on the order of magnitude of 10 to the negative 11th. So what we'll see is the first proton is more readily removed. Let's go ahead and look at a few common polyprotic acids. So what we'll end up seeing, regardless of the acid, Ka1 is going to be usually much greater than Ka2, which will be even greater than Ka3. So the removal of the protons keeps getting more and more difficult. And sometimes what we'll see is there's a couple of things. If an equilibrium constant is not well known, we might just give you a rough estimate. So that's the case for hydrogen sulfide. In the case of sulfuric acid, which is a strong acid, sometimes we don't actually give a Ka value. We might just say that it's very large. And what that's saying is, instead normally how we would write a reversible reaction, we'd have our polyprotic acid, and the removal of this first one, the first proton will give us something that looks like this. So we won't think of that first step as being reversible. We're just saying that the first proton is more or less just given up all the time. So that's a safe assumption for this class whenever we say that there's a strong acid. So this just means that in this case, none of the original acid remains. So now let's go ahead and try an example. So here, let's go ahead and look at a carbonic acid solution. And if you recall from the previous slide and example, that Ka1 is equal to 4.3 times 10 to the negative 7th, and Ka2 is equal to 5.6 times 10 to the negative 11th. So what we're asked to find in this case is the pH and the concentrations of all species present. So what we're going to do is we're going to take this step by step. So the first step will be to look at our acid. So we have carbonic acid dissociating in water. And that will form HCO3- plus H3O+. We set up our ice chart over here. The initial concentration of the carbonic acid is 0.020. We don't have any conjugate base or hydronium. So we'll have our changes minus X plus X. So So we end up with 0.020 minus x, x, and x. Let's go ahead and write out our expression for Ka. So Ka1 is equal to HCO3 minus times H3O plus divided by the concentration of H2CO3. So we can go ahead and plug in. And what we'll end up seeing is whenever we solve for x, x is equal to the concentration of HCO3 minus, and it's also equal to the concentration of hydronium. And in this case, x is equal to 9.3 times 10 to the negative fifth molar. And if we're asked to find the initial concentration, or excuse me, the equilibrium concentration of the carbonic acid, what we'll see is it's essentially the same as what we started with. Whenever you take 0.02 minus 9.3 times 10 to the negative fifth, you end up with the exact same answer. So, we've only answered one part of the question so far. We know the concentration of the carbonic acid. So we need to go through and end up finding HCO3 minus, CO3 minus, and H3O plus. So we actually need to make a second ice chart. So what we'll do is we already know this concentration, and then this should not be H2CO3. This should be HCO3 minus. We know the concentrations of HCO3 minus and H3O plus. We'll set up our second ice chart. So for our second ice chart, we'll start out with HCO3 minus, which will be behaving as our acid, plus H2O. And now this will go on to form CO3 minus plus H3O plus. So recall that we know the concentration of HCO3 minus and H3O plus, so we can plug that 9.3 times 10 to the negative fifth right there. And also right here, this is one of the most common mistakes that people make, is they forget to put down the initial concentration of the hydronium. So we'll go through with our ice chart as usual, minus x, plus x, plus x. So at equilibrium, we have 9.3 times 10 to the negative fifth, x, 9.3 times 10 to the negative fifth, plus x. So let's go ahead and write out our expression for Ka2. And recall that Ka2 is equal to 5.6 times 10 to the negative 11th. So whenever we write out our expression, Ka2 is equal to the concentration of carbonate times the concentration of hydronium over our concentration of HCO3 minus. So whenever we plug in, we'll plug in x for carbonate, and we'll plug in 9.3 times 10 to the negative fifth plus x all over 9.3 times 10 to the negative fifth minus x. You have to make sure that you're following your order of operations and including parentheses whenever you plug this in your calculator, or it's going to give you a very funny answer. So whenever we plug in, we'll end up seeing that x is equal to 5.6 times 10 to the negative 11th. And in this case, x is equal to the concentration of CO3 minus. So one of the nice things here is because Ka2 was on the order of 10 to the negative 11th, and then both of these concentrations were 10 to the negative fifth, we can actually completely ignore these plus x and minus x in the terms. So then the 9.3 times 10 to the negative fifth cancels out in the numerator and denominator, and we're left with x is equal to Ka2. So now what we can do is we can go ahead and show the final concentration of HCO3 minus, H3O plus, and then also we'll calculate the pH. So HCO3 minus and H3O plus are both 9.3 times 10 to the negative fifth. Well, if you add or subtract x, 5.6 times 10 to the negative 11th, they differ by 6 orders of magnitude, so there won't be an appreciable change. So what we'll see is these initial concentrations up here, these are also your final concentrations. And then to find the pH, pH is equal to negative log of H3O plus. So whenever we plug that value in, we'll end up with a value for our pH being 4.0. So let's go ahead and try one more example together, and then that will conclude our practice on polyprotic acids. So here what we want to do is we want to look at finding the pH and the equilibrium concentrations in a sulfuric acid solution. So here, let's go ahead and recall what our Ka values are for sulfuric acid. So Ka1 was very large. Ka2, still a pretty large K value, but it was 1.2 times 10 to the negative second. So this is what we're going to do. Because H2SO4 is a strong acid, and it's going to dissociate completely, we'll say that it will dissociate with water to form H3O plus, and also HSO4 minus. Since it's dissociating completely, the concentrations of H3O plus and HSO4 minus will be 0.10 molar. So we can actually skip to our second ice chart here. So we can look at the removal of the second proton. So we'll start with HSO4 minus plus H2O yields H3O plus SO4 2 minus. And plug in our initial concentrations. So again, recall for HSO4 minus, it's the same concentration as H2SO4 because Ka1 was very large. Same thing for hydronium. And then we'll end up here with 0 for the sulfate ion. So we'll have minus X plus X plus X. So Ka2 is equal to the concentration of our hydronium ion times the concentration of SO4 2 minus all over the concentration of HSO4 minus. So whenever we plug in our equilibrium values, we'll have 0.10 plus X times X divided by 0.10 minus X. Again, order of operations are crucial here. And this is equal to Ka2, which was 1.2 times 10 to the negative second. So when we solve for this, we'll find out that X is equal to 0.0098 molar. So this is our concentration of SO4 2 minus. And then we will just take X value here that we just calculated for and substitute it into the equilibrium expression. So we'll substitute it up there. So that means our concentration of hydronium will be approximately 0.11 molar. Concentration of HSO4 minus will be 0.09 molar approximately. The pH will be 0.96, which makes sense because this is a strong acid, so it should have a lower pH. And then what we'll also see here is since H2SO4 is a strong acid and it dissociates completely, there should be none of this left. So I hope this helps explain polyprotic acids. It's the exact same process as what you've been doing previously for weak acids, except for now you're going to get your initial concentrations for your second proton that you're removing by using the equilibrium concentrations from the removal of the first proton. I hope this helps.